Welcome to 6502 Assembly Language Programming. In this video, we will cover 6502 subroutines and the stack. Now here we are talking about subroutines, the word subroutines, in the context of the 6502 and the DasmJS assembler. A subroutine is a named sequence of instructions that you invoke with the JSR instruction and you return with a RTS instruction, RTS being return from subroutine. The subroutine may perform a frequently used task and be called repeatedly, or it may just have code that you want to encapsulate. If you've been working through the course, you've seen that we have been using subroutines to isolate exercises from the rest of the program. The DASM assembler features a subroutine directive that serves to provide local variable names. For instance, over here, you see the directive subroutine. This does not generate any code. It just establishes a scope for the labels that start with a period. For instance, the dot loop is a local variable to the subroutine. So each of these two subroutines has a dot loop and the dot exit. The 6502 uses the stack to save the return address after a JSR instruction. The stack may also be used to save information and pass parameters. The 6502 features a dedicated stack page, and the stack pointer is actually an 8-bit index into that page. Normally, the 6502 uses the page between hex 100 and hex 1FF for the stack page, but the Atari 2600 uses page 0. That is the region between address 0 and address hexadecimal FF. However, only the range hexadecimal 80 through FF is populated with RAM. So we're going to look at a code example and walk through the methods or a method of passing parameters on the stack. Here we have the code in the initial state. The highlighted, the line that's highlighted in yellow is the line that's about to be executed. And this is the stack initial state. You see that the stack pointer points to address FF. Here we've stepped through the first two instructions, the LDA and the push A. PHA stands for push A. So here's the state of the stack after the first PHA instruction. You can see that the value hex 22 has been written to the stack, and the stack pointer has been adjusted. Note that the stack pointer is always pointing to the next location to be written to. Now here is the code after the second PHA instruction. And here is the state of the stack. Here's the code after the jump to subroutine instruction has been executed. The TSX instruction here transfers the value in the stack pointer to X in order to use zero page X addressing to access the parameters on the stack. So this LDA instruction adds a zero page address 3 to the value in the X register and then loads the A register from that address. The subsequent compare in LDA instructions or load A instructions both use the same addressing scheme. And here is the stack. Here is the return address from the JSR instruction, and you may notice that the return address is stored in low-high format, as it's sometimes called, or little endian format. In other words, the lower order byte is stored first, and then the high order byte. Now we step through a few times, and this is the code after the return from the JSR. At this point, the code is going to clean up the stack to get it back to the initial state, and that's what these two PLAs are about. Now, PLA stands for pull A. However, this is kind of uncommon. Normally, the terminology is push and pop for stacks. Push and pop for stacks. It's not push and pull. So here's the stack situation after the return from the JSR. Now we've executed one of the PLAs, and this is the stack pointer after the first PLA. Now we're stepping past the second PLA, and this is the stack pointer after that. The stack pointer is back to its original value of FF, and the entire stack is once again available. Okay, let's go look at this in the IDE. So here we are at the 8 bits and 1 byte website at the home page, and we're going to navigate to the source code that we need by clicking on Learn 6502, and now course source files, and now resume work. Here we're interested in ex5.asm. That contains the exercise for this video. Now the task is pretty simple. The caller will have pushed 2 parameters onto the stack before calling ex5. We need to add those parameters together and store the result in output 0. But first, let's have a look at this depiction of the stack layout on entry. At stack pointer +1 and 2, we have the return address. At +3 and +4, we have the 2 parameters. So now would be a good time for you to try to solve this exercise. If you want to, pause me here and go have a try at it. Well, welcome back. Let's go ahead and have a look at my solution. But first, let's set up a failure by changing this implemented or not implemented to implemented and clicking run. Just to show that this light will turn red, indicating the test fails, since we're setting X to implemented on exit, but we haven't implemented anything. So let's go back to the source and have a look at my solution. And so let's see that it works. Now you can see that light changed from red to green. And let's go ahead and step through that code so we can understand it. So here, the first thing we're going to do is transfer the stack pointer to X so that we can use base page X addressing. So we'll step over that, and we'll see, looking at the CPU tab, that the base 16, that the X register has FOX7 in it, which is the same as the stack pointer. Let's keep stepping. Now we loaded the A register with the contents of the address formed by this expression, which adds the address 3 to what's in the X register, and the CPU uses that for the effective address. So if you add 3 to Fox 7, you get Fox Able. And if we look at memory in the log tab, you see Fox 0 here, Fox 8 here. Fox Able is this location, which has 2 in it. So we should have 2 in the A register. And in fact we do. So let's continue. Now we're going to perform this add register of the contents of this address, which is going to be 1 greater than the address we just looked at. So looking at memory, it's going to be this location here, which contains 5. So after doing this add, we should have 7 in the A register. And in fact we do. So now we're going to continue. We're going to clear this breakpoint and just click resume. And you can see we still have all green lights of the implemented tests. And I think we're done. So that concludes this video. I hope you derived some benefit from it. If you did, please do click like and subscribe, and have a great day.